So, you know, I'm going to try to be a Time Lord and do the whole whatever, but anyway.
You're not going to screw us, are you?
I'm going to try. That's the whole point of the whole lecture. I'm only half prepared. Part of that may be so that if I'm an idiot, I can have an excuse. But
No, you can blame me, Richard.
I'll try, but I think they won't accept it. So anyway, the culmination of today before the roundtable after lunch is to continue some work started by Vigier in 1999-2000 on tight-bound states in hydrogen, new Bohr orbits below the lowest Bohr orbit. At that time, I thought that was nonsense. How could there be some more Bohr orbits below the lowest, you know, by definition? And he also was using it to try to explain cold fusion, which I also, even to this day, it seems still to be on the foolish parts of fringe. But I won't go into it now. Something happened in 2012 which made me think the theory was worth pursuing. So our challenge is a lot of this is not just atomic nuclear physics, but also a higher dimensional form of M theory. Any of you who have delved into string M theory, you can see that it's quite a menagerie, and they don't fully know what they're doing. They're trying to try everything. They want to find out of the 10 to the Googleplex, or infinite number of dimensions, infinite number of possible string vacuums. They're exploring every which way to try to find the one. So I just took all the pieces that were pertinent to my model off the shelf and used them to develop this new model. We started 100 years ago and before with classical mechanics in a three-dimensional Euclidean space. Einstein and his contemporaries gave us a four-dimensional space for quantum mechanics. That's a second regime. The third regime, where it's suggested that unified field mechanics exists, and the model I'm using is a 12-dimensional one. Just as the tools of quantum mechanics were invisible to classical mechanics, so until now, putatively, the tools of unified field mechanics are invisible to our current thinking in physics. As everyone knows, space-time is considered a stochastic foam with a zero-point field from which virtual particles restricted by the quantum uncertainty principle wink in and out of existence. Zita Bouvet-Gung explained as interaction of a classical particle with the zero-point field. And Peter has extended this nicely with the anti-space model. According to extended, the de Broglie-Bohm theory didn't work very well in 4 dimensions. I extended along with extensions of Kramer's transactional model into a higher dimensional space, and it seems to work a little better. As you may know, hopefully, in the de Broglie-Bohm, there isn't a collapse as in the Copenhagen, but a continuous evolution, where space-time and matter are continuously annihilated and recreated with this evolution governed by a pilot wave or quantum potential. In this model, this backcloth is considered to be a covariant polarized vacuum of the Dirac type. The Dirac vacuum, because its users have applied extended electromagnetic theory, photon mass, and things like that to it, and because of the great success of gauge theory, they've marginalized it. The best evidence for a Dirac vacuum is the Casimir effect. Lesser indicia of the Dirac vacuum are the Zeeman and Aharonov-Bohm effects. putative type-bound state regimes in the hydrogen atom, we're proposing what we're going to do. The culmination of this is to propose experiments that will cross into these other dimensions and demonstrate these additional type-bound state spectral lines in hydrogen. What this means, as I will try to show, is that uncertainty principle is a manifold of finite radius. So there is, we have a three-dimensional asymptotically flat Euclidean space that we observe. Then we have this manifold uncertainty blocking another realm of dimensionality that is, has infinite size. Lisa Randall is one of the major proponents of infinite size extra dimensions. This model does not work in a Big Bang cosmology because of certain inherent parameters in this cosmology. It only works in that cosmology. As if you've dabbled into string theory, you know that Planck constant is no longer fundamental. String tension is a factor added to the Planck constant. I had a little bit of, my model was conflicting with the current string theory a little bit until about a year or so ago I uncovered the original hadronic form of string theory. String tension in the current model is fixed. It's one tension that's fixed for all the strings. In the original hadronic, it fluctuated. And that is much more compatible with my model. And also, the other reason that they rejected the original hadronic form was it had a tachyon. But the tachyon, in terms of a Kramer transactional model where the present is a standing wave of the future past, the tachyon is a key element. The cosmology that kind of is reduced to a rigid Planck barrier. In this model, and as I will tell you, I built part of it on Elizabeth's model. She has an 8 space, a complex 4 space added to the 4 dimensions of Minkowski space. That didn't quite work for me because that other complex space added to it was still came to a rigid barrier. What I needed in this model, it's like it's in, our reality is in free fall. So there are other higher dimensional, a plus and a minus for metaphorically complex space that allows this to be created, our reality to be created and recreated continuously. And that is one of the key elements of this model in order to find the new spectral lines. The other one is, it is mandatory to surmount the uncertainty principle, which, as you all know, has been proven empirically by the Copenhagen interpretation. So we'll go into that a little bit. The trick, or whatever you want to call it, is to do something else. Also, in regards to the Dirac vacuum, some of you who have read a blurb on string theory, you've heard of Calabi-Yau mirror symmetry, a 6 or a 9 dimensional manifold, like a dual 3 torus, and it has a left-right symmetry. String theory is looking for one unique compactification which will give us our 4 space. Usually in physics, you want to make your theory correspond to the existing models. In this continuous state model, it's different. We start with, I have 12 dimensions. The first compactification, you know, there's how these compactify is a little different, but it compactifies 11, 10, 9 down to 0, and then it flips back. That's part of this continuous state standing wave. Elizabeth's one told me, I don't like the idea of this standing wave, it's too simplistic. Well, yes, if you think of it as a string on a musical instrument, a one-dimensional string, that doesn't work. Even a 2-dimensional standing wave on a drum. But if you have a 6 or 9-dimensional hyperspherical standing wave, then you get to have the type of complexity that will allow for this continuous state process. So the other addition to the conformal covariant Dirac polarized vacuum is that it's conformally scale invariant. as we'll show in a minute, this particle in a box, 3 or 4 space, has copies, left-right copies in the Calabi-Yau mirror symmetry up to the 12-dimensional model. And 12 dimensions in this model is the minimum number of dimensions for this higher dimensional copy to be causally free of this one. This will have potentially boon for quantum theory. The last major hurdle for quantum computing is decoherence. So whatever you do to this one up here will have no effect on this one. And because there's some ontological properties, not only decoherence but time relative to decoherence. We won't get into this today, but also you see in this, I should have gotten my laser pointer. Let's see if that doesn't work that way. You see the string tension. You see that string tension has energy and length. I've derived I hope we have time to get to the way I was able to discover a unique string vacuum is by doing an alternative derivation of string tension. Instead of energy over length, I think I put energy over the radius of this cosmological least unit. But the interesting thing here, which we won't get to, you can see the fine structure constant is part of this. If any of you have looked into the constants, you know that the fine structure constant and a lot of the fundamental constants are all derived in terms of each other. When we start looking at this in terms of 6 or 9 dimensional, higher dimensional space, I think we will finally be in the regime where we will find the fundamental nature of the fine structure constant. We didn't touch on this too much, but from Peter's second lecture in his new book, I was delighted to find out that there is, and that algebra already existed that we can use to model this experiment. And we'll get to this towards the latter part of the lecture. There are indicia for this model. One of the main indicia being put forward by people like Nima Akarni-Hamed and Lisa Randall at CERN are to search for artifacts that would be indicative of large-scale extra dimensions. And this isn't the correct type of, this is a cross-section from something else, maybe even a Higgs mechanism, but the idea is they will look for discrepancies in the in collisions that will be indicative of higher dimensions. These have been proposed but not performed. The best indicia for our model, experimentally, is work by Chandler and his colleagues. He's done experiments for the last 10 years on hydrogen, and recently he's done some on titanium. And the beauty of this is he stripped all the electrons off of titanium except one, so in a sense you have a larger hydrogen atom. You want that kind of simplicity. This is in your memory stick, so you can peruse that at your leisure. This in 1999 was part of Vigier's original, which is similar in some ways to the Chandler ideas. A fellow named Corbin noticed that the motion of a point charge in the field of a magnetic dipole at rest is highly relativistic, and the orbits are of nuclear dimensions. The further investigation has been undertaken by Schild, but the most systematic treatment of this problem is given by Barut, a two-body system where magnetic interactions play the most significant role is positronium. Both electron and positron have large magnetic moments which contribute to the second potential well in effective potentials at distances much smaller than the Bohr radius. Barut and his co-workers predicted that the second potential well can support resonances. This, whether this correlates totally with the way I'm trying to take this, I'm not sure, but the reason, the first 10 years of Chandler's experiments, the artifact, they violate QED, quantum electrodynamics. The artifact was so small that most people ignored it. The 2012 experiment, the violation was great enough that people started talking about it. They got a little press, even some people whispered Nobel Prize. But of course, still most of the physics community said it wasn't good enough. And that's the way it is, but it was finally a significant step. Now the reason I think this works, if you have your nucleus there, and this is the first Bohr orbit, in this continuous state process when we get there, behind over the hill of uncertainty into the other dimensions, the little cavity will open. And when you do this experiment, especially if you have more radius if you use a titanium atom, it's going to take the uncertainty, it's going to take the collapse of the wave function a little longer. So you have the first indicia that there's something more than just QED. So I think as that, because of the extra cavity, and this is why I think it's an indicia of our model, you saw what we will send our signal, as you'll see later on, and get the whole cavity. So there will, instead of a cavity of this size, the cavity will be a little bigger and we'll get a new spectral line. If you remember from your high school chemistry, the first Bohr orbit is about 1/2 angstrom and the second Bohr orbit is 2 angstroms. So I didn't finish the approximations here, but I'm assuming that the next 2 or 3 Bohr orbits will be in the lower half of between the first and second configuration of Bohr orbits. As I mentioned a little before, we have to have this multiverse cosmology with the continuous state hypothesis, so we don't get anywhere. We're not going to fully find these additional spectral lines in hydrogen. The least cosmological unit. There has been some work. I found a chapter in an edited collection by a colleague, some of you know him, Minas Kafatos, where the fellow wrote a paper on the size of the least unit. And he essentially kept it Planckian. He jiggered it a little bit, but it was essentially a Planckian size radius of this least unit, tiling the space-time foam. But as I said in this model, we're going to have the least unit is something quite different. Planck, because Planck is not the basement of reality, but we have this continuous cycle from 12 dimensions compactified down to near the 0th dimension and back again, like the flipping of a Riemann sphere from 0 to infinity. The Planck constant becomes an asymptote never reached, a virtual thing never reached, and when it gets down to 0, it rotates back. And so it oscillates in this model from virtual Planck, that's the string addition, Planck constant plus string tension, up to the Lamour radius of the hydrogen atom. My calling it the radius of the hydrogen atom is somewhat arbitrary. I haven't rigorously defined that yet, but it'll be something of that approximation, and that is still quite small. So as some people were talking about cosmology yesterday, you have a fluctuating Planck constant at the bottom, or oscillating, and you have the same thing for lambda, so you have an oscillating lambda. And in this model, all the rest of the multiverse is where the dark energy resides, and that's the thing that it's not a full coupling, so you don't have an infinite mass trying to affect our multiverse segment. And to me, that makes dark energy really, really simple. It of course explains why galactic rotation is uniform like a record, not like a vortex. In this model, the Hubble sphere has a finite radius in time. So there are, in this multiverse, room for an infinite number of nested Hubble spheres, like a stalk on a grape with a whole bunch of grapes on it, each with room for infinite number of nested Hubble spheres, each with their own fine-tuned laws of physics. Fine-tuning I touched a little bit in the book Elizabeth and I did, a holographic entropic multiverse. It has to do partly with it's esoteric to physics at the moment. I made a proportionality where I assumed that the mass of the Earth is order of magnitude tantamount to the mass of all life over its 5 billion year period, and you can get the radius of the Hubble sphere. And because we still have neglected the observer, but this is still a little freaky, but that's part of it. You know, that'll be refined later on. So some other Hubble spheres, which are invisible to us because of the nature of this stock, but there will be a new kind of telescope with unified field mechanics, which will allow us more easily to see some of those other parts. So they're going to have the fine tuning will come up through there, perhaps.
You mentioned something about humans and the light. How does that connect to
I made the outrageous assumption that the mass of the Earth over its 5 billion years of existence was equal to the mass of intelligence, equals MC squared. In my model, mind is not tantamount to brain, but there's a Elan Battelle or a life principle. So you have the same energy residing in living systems. So making that assumption and then doing a proportionality with the mass of the Earth, I was able, you get the Hubble radius, which was, to me, that was kind of curious. But anyway, whether that proves out later, it's still far out. It's extracurricular to this, and I probably shouldn't have even brought it up, but I did want to say something about the multiverse. So one of the main pieces of this is this continuous state hypothesis. So if you've looked at Kramer's transactional model, a present transaction, a point, send out the offer wave and whatever they call the other one, and you get a present transaction as a standing wave of the future past in, of course, this higher dimensional standing wave model. So elevating that to a principle of cosmology and building on Elizabeth's work, as I mentioned, you have our Minkowski, Euclidean Minkowski package here with a retarded and advanced standing wave package that brings us up to cosmological level. And just a metaphor to show how the continuous state, a four-dimensional continuous state was way too primitive, and it ties into Hamilton's, the algebra has closure and you can't escape it. We're going to talk about that a little bit more in a minute. This metaphor came to be by accident. My car had broken down in Tehachapi and I had to buy a new one, and I had to wait 3 hours for the tow truck to come because it was so much in the middle of nowhere. I was near the city of Mojave, where they had practically 1,000 wind generators up on the hill. I spent the first 2 hours just walking around and I kind of got tired of it. But then when I looked up on the hill, there were 2 of these wind generators near each other. One was slightly behind. And I noticed the propellers, as they rotated, periodically they formed, which looked like the face of a cube. I said, well, that's pretty interesting. So this tells something more about reality or fermion vertices. Anyway, blah, blah, blah on that one. So this is the first a step towards trying to show an animated view of what this continuous state process does. So you have a cube in the middle with the hypercube elements on the outside, and they rotate into each other. So we do the same thing from the opposite. So we have a left-right and a top-down version of that. This, even for 4 dimensions, it probably might take another dimension to make this work, but instead, we wanted to rotate into itself like that. More like as a Mobius or a Klein bottle kind of thing to operate. But then with the other 9 dimensions or 8 dimensions, whatever, then you'll begin to get this continuous state property where. One other thing to say about Elizabeth's work, she did About the same time, I think in the late mid-70s, she did a lot of work on superluminal Lorentz boosts. In a superluminal Lorentz boost, the spatial dimension is boosted into a temporal dimension. So what is the spatial dimension at one instant is temporal in the next. And then she extended this to her 8 space, and I didn't get what I wanted. I couldn't get continuous space, continuous cycling out of an 8 space. So I boosted it again. I boosted those temporal dimensions into dimensions of energy. So in that sense, this is still kind of simplistic metaphor, and this is where you can complete the de Broglie-Bohm and Kramer models. Those energy dimensions can be super quantum potential, so you have control factors to run this cycling, which to me is part of the beauty of this. Here again is just a little pun on mirror symmetry. Maybe this is where we are all now and where I want to leave us kicking and screaming or whatever. All right, let me, some of this is been by accident. I had a room. Where are you? Apologize for this. I had a room where the screen would say a mirror, and they're on a couple of ceiling fans with the light in the middle, and then, it's probably obvious to someone like Peter, but the fan in real space was rotating clockwise, and if this will ever come up. The other one in the mirror is counterclockwise, so you have nilpotency. And of course, you heard Peter say that these other dimensions were redundant, but that's fine, because of this whole 12-dimensional structure is a infinite potential that should be nilpotent and redundant, so that there's no conflict. What's going on here? Probably hardly worth it anyway, but I think, to my mind, I like metaphors to start initially. I like to do things conceptually and axiomatically, and then try to get somebody like Peter, Lou, and Elizabeth to help me with the math after. And I think, I'm of the mode that you can make an equation for anything. So to me, it's more valuable initially to go through the conceptuality parts of it and then apply the math to it. Well, this computer is on Alpha Centauri. I don't know what's going on. This is a very simple and small MPEG. It should open right up. The what?
It's in another dimension.
At least one.
We wait 4 years, the signal will arrive.
It does, and you gave it.
No, I didn't. I did not do anything.
I saw you over here wrecking my computer. I'm going to blame, okay, here we go. So now I got 25 copies of it. I wonder if I can run them both at the same time.
45 copies of it.
I'm lying, it's really only 2.
It should play. There.
So this is just, so to me, this is indicative of what's actually happening in,
Froze again.
oh, I gotta, it didn't freeze again, I didn't put the, no, I didn't put the repeat, the loop. So, correct me if I'm wrong, Peter, the one before the mirror is space, the one in the mirror is anti-space, can we say that okay? Well, okay.
Yeah, no reason why not.
And I didn't I forgot to finish this. This is my little laboratory in a school bus at the Noetic Advanced Studies Institute in the Escalante Desert in Utah. If I had this to do over again, I would have put a light up here, which would, in a sense, represent the light that you're going to shine, the electromagnetic wave that we would shine into the cavity. And even these surfaces are even reflective enough. In the one I have at the ceiling fan, I showed you that picture where the wind generator is aligned. When this aligns, when these reflective blades align, you will get a flash of light. And so I thought this was a perfect metaphor, because that's in surmounting the uncertainty principle. We want to find a beat frequency of space-time. We'll get to that, so that when the cavity aligns, and if we send we have to start at one end of our postulated spectrum and over to the other one, when we get the blip, that will be the new spectral line coming out of the cavity. Putatively, of course. I hope when we apply the complex Quaternion-Clifford algebra, it will tell us something about how many doublings of space anti-space there are. If the symmetry just has the couple of doublings up the Calabi-Yau ladder, there should just be 3 lines. The first one will be very easy to find, relatively easy, because the more challenging parts of the spin-spin coupling and spin coupling, et cetera, of this space background won't be fully into effect. Those of you who have seen the high school model of a Bohr orbit, you see the orbits and then they have a little infinity symbol at the top. When you energize the electron enough, it flies off, it's free. So at some point, when we find the large-scale extra dimensions, the signal won't come back. If we do it correctly, because it will have flown into the rest of the multiverse. So as I started to say, we'll start out with 2 or 3, and then if there is another doubling, there could be 5 or 6. It may not be till the 6th dimension that it degenerates into infinity. Anyway, this kind of a basic summary or lead-in to what we're looking for. I should have maybe backed up a little bit, and I need to do a little more on the cosmology of this too. Okay, I don't need that anymore. Where do I want to go? Sorry. As I said, this is not a Big Bang universe, this holographic multiverse. Hubble discovered redshift. He did not discover an expansion of the universe. And there's enough alternatives in this model I've been building that make it a viable alternative. Some of them are good. For example, quasar luminosity can be described in terms of gravitational shock waves. This also heavily on, you get at the observational limit at the Hubble radius, yes, light attenuates to 0. And instead of being by a Doppler expansion, it's because, according to the Proca equation in extended electromagnetic theory, when the photon couples to the vacuum over a cosmological distance, it loses its energy. So that this is the old disregarded tired light model.
Is that the extinction idea, Charles?
Extinction?
Yeah.
No, that's different.
That's different.
Why this computer will not just give me what I want, I don't know. The what?
stress sensor. So the more stress you get, the less responsibility it gets.
It's the Heisenberg uncertainty principle.
Totally.
Is embedded in the software.
I don't want any default program, I want to get rid of this thing. It should have been already open, okay. Let's see, which page do I want? Apologize for being somewhat disorganized. Anyway, I'll give, well, let's go here just for a moment and see if there's anything I want to look at. A little bit about the lease. It's curious that the, I didn't have good enough notes here that the least cosmological unit is almost like is very similar to the logo on the doors to the Radisson unit. I don't know if I can get that.
What does anthropic mean in this particular title? Are you actually going after the anthropic principle?
I am. If mind does not equal brain, a Darwinian, naturalistic, atheistic model, then you need some kind of a life principle to guide, instead of a random evolution, you have a guided evolution, and it's an anthropic holographic principle, quote unquote, putatively, that does that.
I tend to agree with that. There's some reason that there's an increase in complexity.
And Elizabeth and I don't agree on everything, of course, but I equate the anthropic field with the unified field. And one other thing about the unified field, we have, until now, fields are phenomenal. Every field has an exchange quanta. It hasn't been discovered for gravity, and I think quantum gravity is not the regime of integration. It's going to be in the unified field, so it won't be quantized, or will have some kind of pseudo-quantization. The unified field doesn't add a fifth force. It adds a force of coherence, which relates instead to topological charge. Information is transferred ontologically. If you've all seen a Necker cube, and if you stare at it, the central vertices switch. There's no energy transfer there. So it's not an energy, information is transferred, but this is for probably decades in the future when we can finally, I may not find this easily, but the first lead-in to my continuous state, or this multiverse continuous state hypothesis, came from work I did with Kafatos, or he was kind enough to let me work on it with him. He took the Eddington, Dirac, and Wheeler large number hypotheses. This is also in your thumb drive, so you can peruse this later, but let's see if I can find some of the key elements. This one, the ratio of the observable size of the universe to the size of an elementary particle, has these relations of 10 to the 40.
Which is the ratio from the strong to the gravitational force.
Exactly, thank you, Elizabeth. There's another one here where you get to the, so this begins to look like I'm supporting the Big Bang. You have a fundamental point, and then you have a scaling up to a cosmological scale with one particle up to 10 to the 80 particles. You get, skipping through a lot of this, which I said it's in your where you end up is at all levels of scale, the rate of change of expansion, you get the speed of light equal to r dot, the rate of change of scale of the universe. And we use that as we make that into a definition. So what, skipping, what we get out of that is that if you internalize this rate of change of scale of the universe, instead of the same energy, instead of it having to be an energy of expansion, it's an energy of free fall. It's an energy, this continuous state has the same energy, but it's like you're in, I think I have a, you know those, they have them at amusement parks, like the ball goes on the pin raster and it's bouncing down, the ball being maybe some unified field or some particle. But instead of it falling down to a thing, if in this continuous state process, and instead of being a two-dimensional pin raster, if you have a hyperdimensional pin raster, that ball never hits ground because all this stuff is, so in a sense, it's staying right in the center, bouncing around stochastically, which is how it is observed from force space. It's not from the unified field point of view. There's a duality and there's a coherence behind it. But that essentially, and it's a difficult evolution to make this be so, formalize this sufficiently to have it, give it the importance that it needs to have. It's one of the key elements of this cosmology and the major requirement for finding these type-bound states, that there is no expansion, that if you went out to the Hubble radius, you would see out another Hubble radius. It's an observational limit based on attenuation by photon mass. Almost everyone who's done photon mass, they give it an average of 10 to the minus 62 grams or whatever. I do it different because I think, other than that, the speed of light would be infinite. So the photon couples, and when it couples, it has that internal spin. That's its mass moment. The wave, which travels at the speed of light, leapfrogs over that. So you have this. So there's kind of part of the wave-particle duality. The other thing we do here is we elevate wave-particle duality to a principle of cosmology, and that's where you get those three, and that gives us some more interesting. I'm not going to dwell on this because you can read through it at your leisure, but this is where you get to the definition that r dot equals c, and it's internalized in this continuous state, higher dimensional manifold. Here is the Radisson logo. Whoops, where'd you go? Now you're going to be so far away all the time. Sorry. I heard that. Stop. In contemporary physics, we have a rigid vertex singularity point particle. Right here. This is called the Witten vertex, and I put a paper, I think it's called The End of Space-Time. Anyway, there's a paper by Witten on your thumb drive where you can read about this. This is like crystal structure. We have a least unit that the whole crystal is built up. This is an element in the least cosmological unit, but this particular one, this can't, like a quark, cannot exist free in nature. So I tried to put, metaphorically, elements of the psychology. Here's the field. This is the, so you have the wave-particle duality. Here, this is a string, Witten string vertex, so instead of being a rigid point, getting the extra dimension of the string, it allows these things to rotate. The topology, the manifold, they can rotate into each other. These are the control factors, the de Broglie-Bohm quantum, superquantum potential elements that go into this model. Maybe it's just a coincidence, but I love the fact that it looks like the Radisson cross keys, because this is this is maybe even more so than the continuous state cosmology. The least cosmological unit is the biggest key to this whole thing. It's also funny that the fan-blade quaternion model, Lou, Peter, and I are each on different corridors, meeting at the elevator at the core of the quaternion. I'm going to mention Sabah's dream. He got a dream the other night of just kind of a sign with the letters S, P, Q, R. Sabah, Peter, Lou is a Q, and R for Richard. And we Googled that. It turns out to be, for even contemporary Rome has that as part of the thing. I forget exactly what it means, but we're still a little bit at a loss by why Lou should have a Q, but when Ludwig was misspelling his translation from Polish, quantum, with the K for the Polish way of quantum, we have at least a Kaufman element. But anyway, I don't know. I mean, the signs and wonders, who knows? But anyway, let's see. That may be all I want for this.
So did Radisson ever have that thought in mind when they created that logo?
We'll have to go find the guy who started Radisson and see what, well, cross keys, maybe the other Radissons have something different.
Yeah.
It's a good little research project for you, huh?
I'm not that curious.
What can I, here, wait a second. Hey.
Even that
You
doesn't
are
bother
getting
me.
curious anyway. Let's see. That's probably, don't need
So
anything else.
this experiment that you want to conduct out in this is related to this last figure that you put up? The experiment that you like to conduct out at NIST,
Yeah.
I mean, is it related to that configuration that you showed?
Yeah, we need to do more development on that. So I could draw a circle around the Witten vertex and the three control factors. Again, it's nice that it's in threes because that seems to be important. And that would be a sphere, some kind of a sphere, maybe a three-sphere, whatever. But those then need to be close packed. I don't know how to do the close packing yet. I think maybe, I'm hoping that the algebra will suggest how, to what extent the close packing, I have some of those close packings, might as well go there now. Hello, I'm busy. It's my girlfriend. I'm gonna be stupid. Hi, Star, I'm in the middle of giving my unprepared presentation, so I'll have to call you back. Bye-bye. All right, love you, bye. Let's see, where are we? I thought this was a great metaphor for space anti-space. I mean, I like things that kind of stick in the mind. And it was nice that it came, of course, she doesn't look quite like that, but. Another metaphor for
Can you show it again?
hurry.
Thank you very much.
All right. Another metaphor for extra dimensions. You know, we have the quantum barrier, the stochastic quantum manifold of uncertainty. I forget what wisecrack I could make about that one. Okay. So here's the least cosmological unit, and you can put IJKs or whatever in there. So I haven't figured out how, as I said, part of these have to be in the 12-dimensional space with the control factors. So all those dimensions, and they're being boosted. So some are energy, some are time, and how the redundancies work. Maybe it's only a dual Calabi-Yau 3 torus. Maybe there's only 6 spatial dimensions. But it may be from some perspectives in this evolution. I need to figure out how the spheres need to be packed relative to 12 dimensions, so they're causally free. Remember I said the quantum particle or the fermion in the 3-4 space box in this cycle is causally free of the 12-dimensional one. This is how this has to have so that each point in space-time, a la Kramer's transactional model, annihilated, created, annihilated, created, annihilated, and created over and over again, instead of being reduced to basement of reality Planck foam. This annihilation creation of space-time is the most important part of this. Now, I'll just skip around a little bit. The way I see at the moment of this experiment working is another view of that. So here's this view of the manifold of uncertainty. And I did initially a more simplistic, there's a common from the late 1800s way of taking volumes of hyperspheres. And it's curious that after about 9th dimension, yes, Lou?
What do you mean by manifold uncertainty?
Good idea. I can say these days geometric topology, can I? And this, it has partly to do with why there needs to be a barrier between Euclidean space and Calabi-Yau space. But, and I should look at what definition of a manifold maybe I want to use, but it's not, I guess we wouldn't say Euclidean space is a manifold, or we wouldn't say,
Euclidean space
you can?
is a local chart for manifold.
So how many, I guess we're going to start this, if Euclidean space is down here and the higher dimensional Calabi-Yau mirror symmetry is up there. So I think we're going to, and the least units will be cycling through the whole thing, the whole 12-dimensional cycle. Well, but where these are infinite, Euclidean dimensions are infinite size, and I'm proposing, along with people like Lisa Randall, that after you get, I don't know where she starts her infinite size dimensionality, but after, up here someplace, you get infinite dimensionality again. So because, again, I don't know how to define this manifold completely, because it's going to start perhaps at 4 or 5 dimensions, then go maybe to 6 or 7. So that, at least that many dimensions for its radius, and this.
What I'm trying to get at is, where's the concept that gives rise to the manifold uncertainty? We understand what uncertainty means in terms of observation or observation of complementary variables.
Right.
So that's perhaps where we want to start, with the notion of uncertainty. And
Right.
You're saying there is a manifold that's associated with that, and now I have a disconnect.
Yeah, and this is a perfect question, because I'm making this up as I go along, and I'm counting on people like you to criticize me so that these get refined. But part of, and I didn't realize you could call Euclidean space also a manifold, but separating Euclidean space from some cutoff into Calabi-Yau mirror symmetry, higher dimensional brane, which is also a topological manifold, we have some finite dimensionality of maybe 3 or 4 dimensions here. So uncertainty, we look at, we just consider the Minkowski space of quantum mechanics as in the 4 dimensions of the space that as physicists work in. But I'm trying to say, I'm adding, and part of this has to do with surmounting it. You can't, I believe it's impossible to surmount uncertainty in terms of the Copenhagen interpretation in 4 space. So from 4 space on to 6 or 8 dimensions, that's the finite radius of this manifold in the middle of these other domains. And it's like a gate. This is a gate, and the reason it becomes important is we're beginning to add extra dimensions. And let me see if I could zero in this some more.
I got an idea of how to explain it, and I
Okay.
should have had this picture too. You have your regular 4-dimensional manifold that has the Heisenberg uncertainty principle. But then if I have this hyperdimensional space, it maps on to the 4 space as a mapping. Could be a projective geometry. And as that mapping from the hyperdimensional space occurs, it's inaccurate, it's incomplete. And that leads to the Heisenberg uncertainty principle. In other words, in the hyperdimensions, it doesn't occur. It's just the mapping to the lower dimensions is incomplete. And I also should state that the reason I used the 8 space was to have Lorentz invariance consistent with Lorentz invariance, but that doesn't preclude hyperdimensional geometries. Like I did a 12 space too, so that doesn't preclude those other hyperdimensional spaces.
I think in a sense this is probably an 8 space because in the continuous cycle with some of the dimensions being temporal and some of them being energy, that the redundancy of some of the dimensions, but so I think in terms of the least cosmological unit, it takes, even to have anything, in this model to have our 3-4 space, it's a resultant of the whole 12-dimensional cycle. It's collapsed down as a standing wave to our space. I wish I forgot my train of thought. So if this in its own right, so I think it requires some of the Euclidean Minkowski space dimension to operate, and the other ones are still its control factor, but in the midst of that, there's this 3 or 4 dimensional, and maybe that's why spatial, that part of it is spatial. So I'm looking at this as a spatial manifold, but it also has the control dimensions, and because it still has its Euclidean Minkowski space resultant down here, with the superluminal Lorentz boost to temporal, the double superluminal Lorentz boost to energy. The other thing is this requires, surmounting uncertainty requires another transformation beyond the Lorentz point here. There'll be a 12-dimensional transformation that I started to try to do some of that. I don't think we're quite done arguing this. If we just talk about this piece of it, it's an n-dimensional manifold of unknown d, or unknown dimensions, but it doesn't exist by itself. It's a component of all of this other triune structure. But have we gotten there yet, Lou, or are we still? I mean, this is important enough that it should be argued.
At this point, I would listen to you. I won't try to decipher.
Because I've gone so far up into the Netherlands. Euclidean Minkowski space, which, so this is the regime where the type-bound state new spectral lines will occur. Maybe there's one in this, we can use this to say it's a cavity, and another one up here someplace. And then if it is only take Peter's space, anti-space, and double it only once, maybe this is the infinity point where that third spectral line will be degenerate. If this demands another doubling, then it'll be 2 more spectral lines before the 5th or 6th one is degenerate. But these, according to, I'm using, if you use hypercubes, then they're all, like Peter said, the Pythagorean theorem, and they square up. But this, you don't get, you have to use hyperspheres, or it doesn't have the same structure. But anyway, as I started to say, you take the common little formula for calculating the volume of hyperspheres, and so if you add, and I gotta look also, see even the little indicia is, do we calculate the Bohr orbits from 3-dimensional space or from a 4-dimensional? I think it's probably only 3. Is that right, Elizabeth?
I would go from start with that.
3.
So you can compare the spectral.
Yeah, because they're measured in 3 space.
Right, really.
So-
Yeah, because that's like 3 space and time in quantum mechanics,
Yeah.
whereas relativity is 4 space because it's space-time.
So initially, for the first few months, I was making that conceptual error. I was starting with the 5th-dimensional one, but I think the next one, and so that would be compatible with those rotations, and that one's the easy one. So this is 4 dimensions. So and if we then say take this only up to 6 dimensions, then we're compatible with the simplest form of dual Calabi-Yau 3 torus mirror symmetry. So maybe that's a little bit of a conceptual improvement. So this is
If I
4, 5,
visualize
6.
uncertainty as a sphere in
Yeah.
3 dimensions, like I don't know exactly where the electron is, but it's somewhere in the sphere, and then I simply say, I'll add dimensions, is that the kind of thing you're going to?
But they're only added in this Calabi-Yau mirror symmetry. They're not stacked. They're not stacked some way. They convolute so that our package, our 3-4 space package that we live in, what it's made out of at one relativistic instant has boosted to time, to energy, all of the sides of the hyperdimensional structure, they're all continually annihilating, creating, and fluxing through this.
How do you imagine manipulating these boosts so that you'll see a transition?
All right, that'll be one of the next steps when we talk about the experiment. Creativity is an interesting thing. We think of quantum mechanical uncertainty as on a line, I guess, not a point, but we do our quantum mechanics on a line. I found a German, I forget his name, and I should look it up so I memorize it. He quoted some other mathematicians who did quantum mechanical uncertainty on a circle. But his thesis was doing quantum mechanical uncertainty on a Riemann sphere. And to me, that was like a gift from heaven. So because then we have, that ties in with the least cosmological unit. So if we draw this differently, we're going to have, this will be part of this tip of the iceberg that's close packed in that way. And these will all be, so I would think you'll love that thesis. It's on your memory stick. Read that German's thesis of uncertainty on the Riemann sphere, and I think that'll answer your question much better than I can. Maybe this is belabored. This is enough for now. I dabble. I don't know what a manifold is. I kind of know what a manifold is, but I don't. So I need to. So in standard string theory with fixed string tension, you have Planck constant and then the little factor that they add, as we showed the string tension formula earlier, that you add. So if you remember, R1, R2, frets on the instrument, Kramer's standing wave of the future pass, we have in the continuous state, dimensional reduction, spin exchange, dimensional reduction, compactification process through all dimensions, not just one. You have this cycle down to virtual Planck. And then that's the 0 point in the Riemann sphere, and then it flips back up to infinity, and in conjunction with the rotation of the least unit, cycles through this. And until I know better, I'm calling this the Lamore radius of the hydrogen atom. Instead of Planck, I use the Stoney to formulate this because it's electromagnetic rendition. And of course, Planck came on along with the mathematics and stuff that was more used the way that physics evolved, that they kind of threw away the stony for a while. But so this also, in terms of the Dirac polarized vacuum, is amenable to electromagnetic effects. And so we're starting to get to the point where we can see how we can do the experiment. This doesn't fully go with today's talk, but if you know what an exaplex is, an excited complex, it's in chemistry, an exaplex, it will never go back to zero. What we use now in current quantum mechanics is we have virtual particles in the stochastic foam, and this structure goes back to zero. But with an exaplex and the rotation of the least cosmological units in terms of de Broglie, Bowman, Kramer, this continuous state cycle, because this never goes back to zero, you can kick out a proton. You know, if you've ever read Eddington and stuff, you only need one proton for how many cubic kilometers is it? It's an amazing few number of protons that you need. So this is again another support for this multiverse cosmology, because this mechanism, this exaplex mechanism built into the least cosmological units, tessellating space-time, they make it very simple for protons to be kicked for vacuum creation of matter. Just an aside, which I think is very important. And, you know, I'm trying to apply that also to these Bohr orbits. About a couple of months ago, I thought the topic of this colloquium would be to find the algebra. And I was wondrously surprised when I started reading through Peter's lectures and found the complex quaternion Clifford algebra, which is key, which is the algebra that we can develop to use. This isn't the correct Bessel function, but as I said, the first spectral line will be easy to find, and then we'll probably need to apply some kind of a Bessel function to find the others. The simplistic model of the experiment is you have hydrogen in this sample tube, you do your resonances in the way that we'll talk about a little bit, and then you'll get, we'll hopefully get a spectral line. I need to go, all right. This is, I've actually been arguing with Lou and Peter for the last couple years. You know, I never knew, I really thank Peter especially for learning about quaternions and their power. And it helped so much in developing this model, and the idea, and to follow Hamilton's history of, you know, he added one, he added J, and the algebra didn't work because it didn't have closure, it was just a mess. And then he finally had to sacrifice commutivity and close the algebra when he added the K. So you have a cyclic continuous algebra. But I knew, and this is where I tried to argue with Peter and Lou, couldn't get out of this. I can't surmount the uncertainty with using a closed algebra. I needed an algebra because, as I said, I mentioned some of those cyclings that the least cosmological unit has to do, space-time energy, and the compactifications. I needed an algebra that periodically commuted again. You know, you have like a holophone, like a lighthouse, that the idea, and I'm a little bit short on physical reasons at the moment, but if the unified field also contains a life principle, in order for it to get into a living system, the gate has to open and the lighthouse has to flash into a living system. And we don't see that. We're embedded in and made out of this matter. We know this is the surface of electrons and it's 99% empty space, but you know, we don't have the phase possibilities to walk through this. Keep losing my train of thought, sorry. let's go to this then for a moment. There's, in simple mechanics, a thing called perfect rolling motion. You take a logarithmic spiral, you know, this doesn't work because bang, you're down at the Planck scale again. I guess you could flip this, but you cut pieces off the spiral and make these kind of wheels. And they use this in some gearing mechanisms. These, like those wind generators, are going to just most of the time cycle stochastically. But periodically, this is a metaphor for commutivity, anti-commutivity. Periodically, because of perfect rolling motion means no slippage, they will align. One of the best metaphors I like for this is if you've ever been in a graveyard or a fruit orchard, there's places you can see to infinity, places where you're blocked. So the places, this is again like a wave-particle duality, so you get a periodic opening of this with these rollings of the least cosmological units. I'm not going to use this really in this lecture, but these apply a little bit to the Chandler experiment, where you have a little bit of space before the uncertainty principle takes full action, where you can get a little bit of energy that violates the uncertainty principle. This is, again, just a metaphor for the paths that are open. If you're sitting in an auditorium, you see there's one straight ahead, two on the sides, and here. So you have holes in this hyperspherical structure, which is our reality. And again, this is a metaphor for we take our little laser pointer from our R1, R2, and we get to the right point, and we're going to get a blip, which will be the new spectral line. Now a little bit about, I didn't get the experiment into this. I forget when I started. When do I, if anybody has it?
I don't know.
About 5 after 1.
When am I supposed to end? Adding 10 minutes for our delay.
I'd say about 10 after 1.
So I get about 10 minutes?
Yeah.
All right, there's a thing called,
However, those two clocks are not correlated.
10 after 1 now.
there's a thing called, okay,
So you
well,
may
I'll
wanna take the
finish up
average.
in 5 minutes. And we can save any discussion until after lunch at the round table or whatever. I want to talk briefly about the experiment. There's an effect called the Sagnac effect. You take two counter-propagating laser beams, and in the small scale, they violate special relativity. This, again, is probably indicia of a Dirac polarized vacuum. So you can, in a sense, we assume that all matter comes out of spacetime. Matter comes out of spacetime. So we have a mechanism that will interfere with spacetime, this beat frequency of these least cosmological units. We need to derive the beat frequency by once we figure out how to close pack these spheres. Once we know the size of the minimal least unit, then its relativistic motion will give us the beat frequency. So a fellow in Belgium, Daniel Dubois, he talked about incursive oscillators. And so you get a delta T. The delta T would be the size of the hole in one punch relative to this experiment. So I take, initially, whatever atom I'm going to use to do this experiment. In this case, I guess it's going to be hydrogen. And I start my resonance hierarchy that will jiggle the electrons. And I make that resonance hierarchy such that that jiggling of the electrons will jiggle the nucleons. Then in order to do the rest of it, I have to know something about my beat frequency. Then I'm going to, so it's a hierarchy. This is they send out a continuous field arbitrary along the z-axis, and you get the separation of states in the Stern-Gerlach apparatus. That was the historical demonstration today, the solid, beautiful empirical proof of the uncertainty principle. So this is the part of the do something else. If it wasn't, and this is why you have to have this cosmology. There's no continuous state. There's no gap behind this. There's no beat frequency in our current standard models. So